Okay. Okay, so some of them did extend over New Year's. Oh, that's nice.
We had like moratorium, Christmas, practice, game, practice, like 2 days.
And then, they split it up. That's interesting. Okay. Hey, so guys, this is what we're up to today. The date is the 8th. It's amazing. We're already a week into January, and we're just getting back. That's a sign of a good Christmas break. So guys, today what we're going to do is we're going to start this unit by talking about molecular polarity. What you're going to find is that traditionally, this is one of my students' favorite units. Probably second to electrons, things, and stuff like that. But guys, this is a very, very practical unit. But in order to understand the practical side to this, we need to reach backwards and look into the previous unit. And guys, I know that was before Christmas break, and you remember very, very little. So guys, this works out well because literally the majority of the day today, we are going to reach backwards into the previous unit, and we're going to talk about what you do and don't need to remember. Then, guys, it's going to get practical for a minute. We're going to draw like 6 Lewis dot structures. Then we're going to add 1 new idea to that, and then you're going to have time to work on your homework today. You guys ready to go? Okay, so guys, this is the way this starts. Let's reach back a little bit and talk about where we came from. So guys, on the last test, we did this. We talked about Lewis dot structures. We talked about names and angles. And guys, I alluded to this a minute ago, but you do need to be able to draw Lewis dot structures, but you ain't got to be able to come up with the names and angles. Guys, those are all gone now. You don't need to remember any of the names or any of the angles. But this is what you do need to be able to do. You should be able to look at this molecule, CH2O, and you should be able to look at this and go, wait a second, these things spread out as much as they can, and so it's not 90-degree angles, it's 120-degree angles. So you should be able to eyeball that and know that this is not what it actually looks like. But guys, you don't have to give it a name, you don't have to give it an angle. So that's thought number 1. Stop me if you need. Guys, thought number 2 is this. In that lab that we did clear back in December, guys, we drew all these Lewis dot structures, gave them names, gave them angles. But guys, we talked about the idea of symmetry. And remember, we said symmetry means the same all the way around. It's balanced. And so, guys, we're going to talk about that today, and you'll see how we're going to do that in just a minute. And then, guys, the last thing that we need to talk about from the previous unit is this idea of polar covalent bonding. And this is not the review we're going to do. We're going to go back and touch on it more. But, guys, we need to go back. We talked about this idea of dipoles and polar covalent bonding. We did it, and we said, don't worry about it. It's not on the test. It's in the next unit, but that's today. So, guys, that's what we're going to do today. We're going to reach back. We're going to talk about some things. We're going to draw some Lewis dot structures. Then we're going to add symmetry to the puzzle. Dang, this is going to go fast, and you're going to be able to work on your homework. You guys ready to go? Goes like this. So guys, again, this idea of dipoles, sharing, and we're going to get into that as well. So guys, here we go. So this is what we're going to do today. First of all, we're going to connect Lewis dot structures with what they actually look like three-dimensionally. Again, no names, no angles. Just be able to picture them. Then guys, we're going to talk polar covalent bonding. Then we're going to bring this together and talk about polarities. So guys, it starts like this. This is where you get going. So guys, draw these 5, 6 Lewis dot structures in your notes. Make them big, however. Make them like 2 inches across. Make them big. Maybe even a little bigger. Maybe you take up half the page doing these. But guys, draw these Lewis dot structures. But guys, what we're going to do is we're going to do these one at a time. So what I'm not saying is don't jump in and do all 6. Do number 1, then we'll talk about it. Then we'll do number 2, and we'll step forward from there. So guys, I am realizing that because we had Christmas break in between, maybe it would be wise for us to do the first one together. just to prime the pump a little bit. So guys, let's do that just to make sure we remember how to do these. So guys, when we look at something like CCl4, guys, remember the rules. We put them on the paper first, and remember carbon loves to be in the middle, and chlorine cannot be in the middle because it's a halogen, group 7. So guys, we go like this. We go carbon, and then we stick our 4 chlorines on the carbon. Then at that point, we count up valence electrons. You may remember that carbon has 4 outside valence electrons. Chlorine has 7, but there's 4 of them, so that would be 28. And we add all of those up, and that gives us 32. Why does that seem wrong? That's right, right? Can I still do math? I think so. Then, guys, we've got to subtract the ones that are already on the page. Each bond represents 2, so that would be a total of 8, and that leaves us with a total of 24. Is this starting to come back to you a little bit? Then what we do is we place those 24 electrons around the molecule. Remember, we have to fill the halogens first, so we go 1 and 2, 3 and 4, 5 and 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That got really ugly, but you get the idea. And guys, that would be CCl4. How's that sit? Is that okay? Now, guys, understand you don't need to be able to say that this is tetrahedral. And you don't need to know that these are 109.5 degree angles. But, guys, you should be able to picture a tetrahedron in your mind and realize there are no 90 degree angles in this, that it spreads out 3. Can you picture you've built? Okay. So, guys, this then is what we're going to do. And this is how we're going to handle the rest of these. We are drawing dots, just a second. Guys, what we're going to do is we're going to draw their Lewis dot structures then as 3-dimensionally accurately as possible. And guys, this is the way we're going to draw things that are tetrahedral. That is the closest we can get in 2-dimensional space to the 3-dimensional reality. Is that enough review? Are we okay? So guys, do carbon dioxide. Draw carbon dioxide's Lewis dot structure. Say what?
On the preview, that molecule 3D structure thing,
Yeah.
it looked like complete and utter insanity, and now I know why.
So guys, carbon dioxide, carbon's in the middle and oxygen on each side. Carbon has 4 valence electrons, oxygen has 6 times 2. Give you another second to complete this one, and then I'll show it to you. You okay? So guys, this is carbon dioxide. It looks like this. You've got a carbon double bonded to 2 oxygens. Notice that each of those oxygens is double bonded to that central carbon, and carbon dioxide looks like this. But guys, we can do better. And some of you are looking at this with a little bit of a frown on your face going, wait a second, that's not the way I drew this. So guys, let's be clear. Is this correct? Yeah, absolutely. But guys, we also understand that carbon dioxide really doesn't look quite like this. So guys, again, you don't need to know the name of this. But guys, what do we call a molecule with 2 bonding domains? What structure will that take on? Linear. And guys, this ain't linear. So what we're going to do is we're going to honor the fact that this molecule is actually linear, and we are going to draw it so that it looks as linear as we can make it. So guys, if you drew carbon dioxide like this, redraw it like that, because we're going to try to represent these as 3-dimensionally accurate as we can. That's the new idea. We're going to draw these as 3-dimensionally accurate as possible. Good? Next one. Water. You can probably just draw this without having to count electrons. guys, for some of you, this may get a little bit sort of ridiculous and frustrating, but oh, look, that's water. And guys, that is definitely water. That is the proper Lewis dot structure for water, but it is not as accurate as possible, right? Because what does water actually look like? It's bent. And so guys, if you're not catching the idea, these two unbonded pairs of electrons bend the hydrogens down. And so water actually looks like this. Again, you don't need to know it's called bent. You don't need to know the angles are less than 109.5. You just got to be able to look at this and go, this is not the best way to draw water. And so we're going to redraw water like this so that it actually looks bent. You guys are doing, so any of you actually get up at all over Christmas break when it was still dark? You did? Why? Good night. Yeah?
I straight up had no choice because my older brother,
Yeah.
Christmas, for some dumb reason, my Aunt Laura gave him
A guitar.
Viking horn,
Oh, shoot.
which was a giant steak.
Yes. Viking horns are horrible Christmas gifts. Not good. I'm sorry you experienced that. You guys good to go? Are we getting the idea here about drawing them three-dimensionally accurate? So guys, these last three then model the way that we're going to try to do these best. So let's do NH3. And I suspect that if you were given a couple seconds, these are hydrogens. They only create single bonds. So guys, NH3 looks like this. But now we need to talk about how we're going to represent this thing. Because guys, NH3 has no 90-degree angles in it. We understand, without needing to know the name, that this is trigonal pyramid. And guys, this is the best we can do. This is the way we're going to draw a trigonal pyramid. There are actually other ways to do this. They're called stereo diagrams. You learn about them in college. But guys, that's going to be good enough for us. We just need to understand those actually aren't 90-degree angles. So then guys, HCl, scratch it down, looks like this. You got a hydrogen, you got a chlorine. That thing is straight. The very best thing we can do is draw that straight, and it looks like this. Now guys, we got to slow down. CH2O. So guys, in a CH2O molecule, we've got the central carbon surrounded by two hydrogens and an oxygen. And guys, I would encourage you not to draw this yet, unless you want to erase it and change it. Because guys, this is one of those that we could actually draw better. Because guys, we understand, we don't need to know the name, but we know that this is trigonal planar. It's flat, but these things spread out as much as possible. It actually looks like that in three-dimensional space. So guys, that's the way we're going to draw it. When we have things that are trigonal planar, we're actually going to draw it like this. And this is what you should draw in your notes. Guys, we're actually going to draw it like this because this gives us a better sense of that trigonal planar structure. So guys, there you have it. That was big idea number one, this idea of drawing Lewis dot structures, but doing them as three-dimensionally accurately as possible. Thoughts or questions? Is it coming back to you a little bit? A little bit? We going to be okay? You guys good? Okay, so now guys, stop taking notes for a minute. What we need to do now is we need to take, and this is actually where we're going to finish today, with these Lewis dot structures. Guys, what we've got to do is we've got to take these Lewis dot structures and we've got to add one new idea to them, and that is the idea of polar covalent bonding. Guys, don't write this down. Let me refresh your memory. Then we're going to come back to the drawings that we did, and we're going to wrap up the day. So guys, it goes like this. Polar covalent bonding happens when you've got two nonmetals. And so guys, they're nonmetals, which means they're strong, which means they fight, which means they share. But the fact is that they're different. And because they're different, they don't share equally. And this is what creates what are called dipoles. Now, guys, dipoles are simply a partial charge on a bond created by unequal sharing. And you're going, wait a second, I don't exactly understand what this is. Guys, let me show you what it is, and let me show you how we deal with it. So grab your periodic tables, flip them over onto the back, find oxygen, find fluorine. Remember the trends on the periodic table. As you move down, they get bigger and weaker. As you move to the right, they get smaller and stronger. So guys, finding oxygen and fluorine, who's stronger? So we got oxygen, we got fluorine. As we move to the right, they get stronger. So fluorine will be stronger. Let's apply that here. So guys, when they start fighting over electrons, it goes like this. This one goes, mine. And fluorine pulls on oxygen's electron. And then the oxygen goes, mine. And it pulls on fluorine's electron. But notice where the electrons are. Closer to the fluorine. Why? Fluorine's stronger. And so guys, when this then forms a bond, they close down. But guys, notice the electrons are closer to the fluorine. That creates what are called dipoles. The idea, guys, is that the electrons are negative, they're closer to the fluorine. So this end is slightly negative and this end is slightly positive because the electrons are closer to the fluorine. Does that sit okay? So guys, how do we represent this? And the answer is we draw an arrow. We draw an arrow that represents the direction that the electrons drift. And then to get really creative, guys, what we do is this. We cross the end of the arrow, meaning that this side is positive and this side is negative because that's the direction the electrons drift. But guys, all you've got to know is you always draw the arrow towards the more electronegative element, the stronger element. That's all you got to do. You guys good? We're done. Guys, that's it. Those are all the bits of information that you need to know in order to do what we're doing today. But guys, let me pull this together for you and explain to you how this works. So guys, if you want, these are the steps, so to speak, in order to do these. If you want to write them down, fine. If not, you'll be okay. But we will be using these steps as we work through some examples. So guys, step number 1 is this. Draw the Lewis dot structure as realistically as possible. Some of you are writing these down, so I'll slow down so you can write them down. So guys, step number 1, draw the Lewis dot structure as realistically as possible. Then guys, step 2, draw the polarity arrows for each one of the bonds. And then guys, step 3, and this is going to seem big, it's a lot of words, but you're going to understand it really quickly. Then what you've got to do is you need to figure out if the molecule is polar. By the way, guys, in homework, there's a question in the homework that encourages you to see the patterns. This could be a little tricky at first, but you're going to find, guys, there are some shortcuts to figuring out symmetry. But I'm not going to give them to you now. I'm going to let you figure them out while you're doing the homework, and then we'll talk on Wednesday. So, guys, what you're going to do is you're going to figure out if these molecules are symmetrical. And then, guys, the answer is yes or no, right? Just like in the lab that we did. I know you don't remember, but that lab where we were building the models. Guys, the answer is yes or no. Is it symmetrical? Yes or no? If the answer is yes, then it's nonpolar, and you write nonpolar. So, guys, you could just write down yes. Here, let's do this. I'm going to add a bit to this just to make your notes easier. So it goes like this. If yes equals non... Oh, I like that that's underlined. I don't even know why that happened. If yes... Oh, now I know. Yeah, we'll leave it underlined. If no... Draw an overall arrow. Guys, that's all you need to write down. So it goes like this. Question, is the molecule symmetrical? If it's yes, you just write nonpolar. Then, if the molecule is imbalanced, if it's not symmetrical, that guy's polar, and you use an arrow to represent the overall polarity. I know that's a lot of words, but it's basically this. Guys, if it is not symmetrical, just draw in the overall arrow. I know that seems like a lot, but guys, you're going to see this is pretty straightforward. So what we're going to do now is we're going to go up to the 6 molecules that we just drew, and we're going to do this to them. We've already done step 1. We've already drawn them 3-dimensionally as realistic as possible. Now all we got to do is draw in the polarity arrows and identify whether the molecule is polar. So guys, we're going to do that. Dang. And then you're going to work on homework. Let you catch up. You guys okay? Okay. Here we go. Guys, number 1, going back up to CCl4. Here's the process. Guys, grab your periodic tables, looking on the back, which one is more electronegative, the carbon or the chlorine? And you'll notice that this one's a little tricky because chlorine is to the right, should be more electronegative, but carbon is above it, which could make it more electronegative. So guys, if you're not sure, what do? Just look up the numbers. Carbon is 2.5. I may have just made that up. Is that right?
Yeah.
2.5. And chlorine, is it in the 3s? 3.1? Oh, not bad. All right, so guys, chlorine is 3.16. Carbon is 2.55. All you got to know is chlorine is stronger. And then, guys, all you do is this. Literally, draw arrows. Draw arrows that point to the chlorines. Guys, what these arrows represent is the fact that the chlorines are literally tugging at this carbon in all 4 directions. Again, all that you did was drew arrows at the more electronegative element and then crossed the other end, indicating that the carbon would therefore be a little bit positive and all the chlorines are a little bit negative. So now, guys, step number 3 is just this. You look at this molecule and you ask yourself a question. Are these poles balanced? Do all of these poles balance out? Is it symmetrical? Yeah, it is. And so, guys, what that means is the molecule is nonpolar. So if all the poles balance out, that makes the molecule nonpolar. Now, guys, a little foreshadowing into what this means as we're getting into this unit. Guys, what that tells us is that this is a gas. Nonpolar molecules form gases. And you're going to find out a lot of the things that this substance does are all based upon the fact that it's nonpolar, and that's where we're headed with this down the road. You doing okay with the process? Let's do another one. Was it carbon dioxide next? Is that, yep, okay, so guys, carbon dioxide. Again, as 3-dimensionally accurate as possible, find carbon, find oxygen, which one's stronger? Oxygen is further to the right, yeah? So guys, what we do is we draw an arrow. Uh-oh, that's not an arrow. Hang on, here we go. All right, this could freak out, wait for it. It did freak out, but now we're back. Okay, so guys, this arrow goes towards the oxygen. This arrow goes towards the oxygen. The guys, do those poles cancel out? Is it symmetrical? Yeah. Therefore, it's nonpolar. But guys, just like CCl4 is nonpolar and therefore a gas, what about CO2? Oh my gosh, carbon dioxide's a gas. Who knew? But now you know why. Guys, carbon dioxide is a gas because it's nonpolar. Starting to get the idea? Let's do one more. Let's do the rest of them. So this should work. That didn't work. There we go. All right, so guys, looking at water, remember the deal. If we draw water like this, we're stuck. Because if we draw water like this, it's going to look like the poles are balancing each other out, which is why it's important that we draw water three-dimensionally as accurate as possible, as we did. Because when we do it like this, we can now see that the poles don't balance out. So guys, which one is stronger, oxygen or hydrogen? Isn't hydrogen like 2.2? Is that true? Yeah. And I know that oxygen's in the 3s. So guys, draw your arrows in without me. What direction do these two arrows go? Towards the oxygen? Okay. So this one goes to the left, and this one goes up. Now, are those arrows, those movements, are those forces, are they balanced? They are not. So now, guys, here's what you've got to do in your brain, and I'll do it on the screen. Guys, you need to think about moving to the left, and you need to think about moving up. And when left and up come together, what do they add up to? Diagonally up and to the left. And guys, that's what you're going to draw into your water molecule. This thing is not symmetrical, and up and left add up to up and left. Guys, understand, you don't draw these arrows. You already did. They're right here. But the overall polarity of this molecule is up and left towards the oxygen. Yeah. Brilliant. And that's what, exactly. So Abby's saying, well, wait a second. What if you put the hydrogen here and the oxygen there? Then this guy is going in this direction. This guy's going in this direction. So then the polarity would be that way. Yep. So guys, then the question becomes, so what? So guys, water is polar. So what? Well, it's a liquid, and it dissolves things, and it does all the magical things that water does. But guys, it's all because it's polar. If water magically became linear and was no longer polar, we would all die in a matter of minutes. Guys, all of the oceans would boil, and it'd be a mess. So guys, everything that we need, that we know to be true about water, is all because it is polar. So guys, the next one we're going to do is what? NH3? Am I drawing dots? Oh, come on, little fella. Hey, there we go, NH3. Guys, try this one on your own. Find nitrogen, find hydrogen, draw in the arrows. This is proving to be a not bad way to start the new year. Not bad. And then, guys, I'm going to sort of let you try this on your own. If all those poles are balanced, it's non-polar. If they're not balanced, it's polar. And draw in the polarity arrow. So guys, let's take it from the start. Nitrogen is stronger, right? I don't remember its number, but I think, yeah. Okay, so nitrogen is stronger. So this bond is moving towards the nitrogen. This bond is moving towards the nitrogen. This bond is moving towards the nitrogen. Now, are they all balanced? They're not. And so guys, what we've got to do is we have got to add up to the right, to the left, and up. And guys, if we add those three things up, what is the overall movement? Up. If we've got in and up, the overall movement is up. So we draw a polarity arrow right through the gut of the molecule, and that thing is polar in this direction. Again, guys, as we're going to learn, that means it's a liquid. It's actually ammonia, and ammonia is a liquid. And in addition to that, guys, ammonia is a really good cleaner. The reason is because these polar ammonia molecules grab a hold of dirt and they dissolve them. And that makes it a good cleaner. So now, guys, HCl. Which is stronger, chlorine or hydrogen? Chlorine. Ready? Done. There's only one bond. So guys, the polarity of the bond is the polarity of the molecule. because there's nothing else going on.
But it is polar.
Oh, yeah. Yeah, this is hydrochloric acid. And all the things that this does as an acid is because it's polar. Yep. You guys ready for the last one, the tricky one? So guys, it goes like this. This is formaldehyde, the stuff that we soak dead stuff in biology so it doesn't rot. But guys, you get halfway there. Draw in the polarity arrows for the bonds. Katie, is this coming back to you? Good. So guys, help me through this. Carbon, a little bit more than hydrogen, right? It's like 2.2 and 2.5. Okay, so guys, this bond, let me clean up my mess. This bond towards the carbon, this bond towards the carbon, but then oxygen is stronger than carbon, yeah? Yeah, so this one goes this way. So guys, what is the overall flow of those three arrows? To the right. That is the overall polarity of that molecule. Again, it's formaldehyde. It's a liquid. It's a preservative, but it's a liquid because it's polar. You guys doing okay? Thoughts, questions, things to chat about? Okay, so guys, that's it. I'm going to hand out your homework packet. You know the drill. This is the packet for the entire unit. Guys, we're just doing assignment 1. It's 1 page. You're going to need another sheet of paper to do this. So here, let me stop recording. I'll get these in your hands. And then, guys, you know the drill. You're welcome to work with the person next to you on these. I'll put the answers up on the wall, and you have the rest of the time to get these done.